Okay, guys, so yesterday we tried the little remote classroom virtual class. Didn't work. That's okay. So here's the video from what we would have done. And hopefully you tried the stamp and this will kind of help connect the pieces. So this was the bell work yesterday. I'll leave number one. Number one is part of review, but where we are going with this stuff starts with 2, 3, and 4. Okay. Number 2 is saying there's some angle in here that if I take the sine of it, I would get a positive 1/2. Okay, what we can think of when we do this is, well, sine is the y-coordinate on the unit circle. So when is the y-coordinate positive? Well, the y-coordinate would be positive in the first and second quadrant. Okay, sine is opposite over hypotenuse, opposite over hypotenuse, opposite over hypotenuse. We're looking for angles. This will give two. This will give two of the angles we're looking for. The first one is 30 degrees or pi over 6 radians. Usually when we're dealing with a unit circle and circles in general, we use radians. The other one is going to be all the way over 6 pi over 6. Back it up one. 5 pi over 6. Okay, that's 2 times where the sine of that angle would be 1/2. But I asked for 3. How can we find the other? And if you just happen to look at the word right underneath this, that gives us our answer. Coterminal. Okay, what other angle could I do to plug into my calculator and make this happen? Well, if I go all the way around the circle again, which is 12 pi over 6, and then I go another pi over 6, that's 13 pi over 6. If I got on my calculator in radian mode, and I put in the sine of 13 pi over 6, it would say 1/2. There's 3 values. Okay, well, 5 pi over 6 would work, and anything coterminal with 5 pi over 6 would work. So I could just add 12 pi over 6 to that as many times as I want. 17 pi over 6, 29 pi over 6, so on and so forth. Okay, I can get an infinite number. I can keep going around the circle over and over and over and make this happen. Okay, so we listed 3. Let's go down to number 3. Well, in radian language, this succinctly describes how to find coterminal angles. Okay, well, coterminal angles are whatever angle you're at plus 2 pi over and over and over. So we can add 2 pi multiple times. Multiple times. Bad handwriting there, but it says multiple times. And I don't have to add. Adding 2 pi goes in the positive direction around the circle again, but I could subtract 2 pi and go around in the opposite direction as well, and that would still give me a coterminal angle. So we can add or subtract 2 pi multiple times to make that happen. Okay. Next, 4. If n represents any integer, so 1, 2, 3, -1, -2, -3, write an expression for 4 pi over 7 and all the angles coterminal with it. Okay, so 4 pi over 7, and I want to add 2 pi over and over and over. Okay, so I'm going to start with my answer, 4 pi over 7, and I want to add 2 pi. Okay, that would be 1. But I want all of them, so I could add 2 pi again. That would be 2 pi's. And I want to add 2 pi again, or subtract. That would be 3 2 pi's, 4 2 pi's, 5 2 pi's. That number, that multiple times, that multiple number of 2 pi's, we are going to use an n for. So if I wanted 4 pi over 7 and all the possible coterminal angles with 4 pi over 7, I could write 4 pi over 7 plus 2 pi n, where n is an integer. From now on, that's kind of an understanding in this class and in math classes in general. And when we write problems like this is called a general solution. N will just be any integer, positive or negative. If it was -5, that would be like going around the circle in the opposite direction 5 times to get all these coterminal angles. It could be a +2, go around twice, +7, go around 7 times. This will give me all coterminal angles with 4 pi over 7 and 4 pi over 7 itself. If n is an integer, n could be 0, and then I would just have 4 pi over 7. Okay. Really good bell work for where we are going with this stuff. So let's go ahead and get there. We're at the 5-minute mark of this video. I'm trying to do this in under 15 minutes to see if we can do it. So we're moving on to 5-3. We'll get a lot of practice with 5-1 and 5-2, so don't freak out if you're still not getting those. We need to sit down and experience a bunch of those problems for sure. But we are moving on here with the type of days we're having right now, this little remote day, so some new notes could do as well. We're solving equations. Just like you solved the equations in Algebra 1, just like you solve the equations in Algebra 2. We are solving trigonometric equations, and just like those other ones, we have to isolate the variable. We have to get x by itself. So to do that, I'm going to add 1, I'm going to divide by 2, and I have this. Should look familiar. We just did this in our bell work. Okay. The difference being, a lot of you from this step will want to say, well, if we're trying to isolate x, Mr. Edwards, shouldn't I just take an inverse sine to the other side, the arc sine of 1/2? But if you remember, when we deal with inverses, we'll only get a single answer. We restricted our domain between negative 90 and 90, so we're only going to get one answer if we take an inverse sine right there, an acute answer. But that's not what we want. We want all the values. Solve for x means give me all the values for x that could ever make this happen. Okay, well, think about what we just did. If I go around the circle once, it's going to happen twice. It's going to happen here at pi over 6, just like the triangle I drew a second ago. And it's going to happen here at 5 pi over 6. And all the coterminal angles with these things. Pi over 6 would work, but 13 pi over 6 would work as well. And 25 pi over 6 would work as well. And 37 pi over 6 would work as well. We need to be able to list all of them forever. Going the opposite way too. Negative 11 pi over 6 would work. So on and so forth. So now we're going to put together everything we did with our bell work, and we want to write a general equation that will give me pi over 6 and all of its coterminal angles, and 5 pi over 6 and all of its coterminal angles. Okay, so here's a picture of me showing you coterminal. Sine of this angle, 390, would still be 1/2. The sine of 510 would still be 1/2. So we need to include those in our answer. To do that, we list the smallest one, or the first one that we found, pi over 6, and then add a certain number of times around the circle, coterminal angles. We list the other one, 5 pi over 6, and a certain number of times around the circle. This is called a general solution. It will give me all answers forever that would make that happen. That's what we're looking for in these. We're solving equations and figuring out when this would happen forever. Something I do want to mention here, there's no symmetry between answers. These two answers work. And this was pi over 6, and this was 5 pi over 6. The distance between this, the number of degrees or the number of radians between pi over 6 and 5 pi over 6, that's 4 pi over 6. That's different than the amount I would have to go between 5 pi over 6 and the next one, which is 13 pi over 6. Those are not the same. That's why I have to list each one of these. But what you're going to see in this next example is sometimes there's symmetry involved, and we can write these answers neater with more, a little more detail without having to write all the answers out. More efficiently, I guess is the word I want. Okay, so let's try the next example. We're at 8 minutes. We would like to solve this equation for x. Okay. It looks a little funny, but just like in Algebra 1 and Algebra 2, we need to combine like terms. I need to get all my sine x's on the same side. So to do that, I would just pick up this minus sine of x and add it over here. Sine x plus another sine x, 2 sine x. I would move this plus root 2 to the other side and get a negative root 2. Easy enough. We combine like terms. Now to isolate sine of x, we're going to divide by 2. Hopefully at this point, you're thinking, it has something to do with 45 degrees. Root 2 over 2. If you unrationalize that, would be 1 over the square root of 2, and it is a 1 square root of 2. That's our 45 degrees. But it's negative. So this time when I draw my triangles to figure out where this happens, sine is negative down here and down here. So if this is my reference angle is 45 degrees, or my reference angle is pi over 4. From here to here is 4 pi over 4, but I want another one. That's 5 pi over 4. From here all the way around would be 8 pi over 4, but I want to back it up one. So that would be 7 pi over 4. So we get those two answers. And what else? Coterminal. All the angles that are coterminal with those two angles would work as well. Would solve this equation up here. So here's the same drawing I just did. I like doing it in real time for some reason. There's no symmetry again. From 5 to 7 is 2. From 7 on to the next one, which would be 17, is more than 2. There's no symmetry. The distance from here to here is not the same as the distance from here to here. So I can't use that efficient symmetry that I was talking about. So we just write each one and add, go around the circle a certain number of times. Okay. Next, let's try this one. You see we get little wrinkles every time on these. This will be a little wrinkle. Now we have a squared to deal with. That's okay. We can handle that. I'm still going to add 1. I'm going to divide by 3. And then to undo a squared, just like you did in Algebra 2, you would take the square root of both sides. Okay, if I take the square root of both sides, I'll just get tangent x on this side. I'll get the square root of 1 on this side. The square root of 1 is 1. And square root of 3 is just the square root of 3. Now something else maybe you don't remember that you need some refresher on. If you take the square root of both sides of an equation, x squared equals 100. If I took the square root of both sides, there's actually 2 answers. I could plug in x equals a positive 10 or a negative 10. When you have to put a square root on something that wasn't originally there, you have to put a plus or minus symbol in front of it. 10 squared is 100. Negative 10 squared is 100. You need this plus or minus symbol, and that's going to happen here. When we take the square root of both sides, I can put plus or minus in front of my answer right here. So the tangent of x will equal plus or minus root 1 over root 3. That actually gives us 4 triangles, right? It's asking us, when is tangent positive? Well, tangent was positive. All students take calculus. Tangent's positive here, and tangent's positive here. Okay, but when is tangent negative? Okay, well, tangent's negative here, and tangent's negative is here. It kind of looks like a TIE fighter from Star Wars. I usually call them that. Okay? Well, let's figure out what angles we're talking about, because that's the whole goal, is to figure out what angles make this happen. I want opposite over adjacent, because it's tangent. Opposite over adjacent. Okay, yeah, that's a 1, 2, square root of 3. We're talking 60 degrees, or 30 degrees, sorry, which is pi over 6. These are pi's over 6. This one is pi over 6. This one is 5 pi over 6. This one is 7 pi over 6. This one is 11 pi over 6. Okay? Now, our first instinct, based on what we've been doing with these problems, is to just list this one and then say plus 2 pi n. And then list this one and say 2 pi n. This one, 2 pi n. This one, 2 pi n. And technically, you would be right, but that's like repeating yourself. When I say 5 pi over 6, there's an easier way to write it. I want to say it's not repeating yourself, but it's writing more than you need to because there's symmetry involved in this one. And my drawing isn't a very good drawing. I'm going to redo my drawing. If it's 30 degrees, it actually looks like this, or more like that. Okay, so now we're talking symmetry. The distance between pi over 6 and 5 pi over 6 is 4 pi over 6. And the distance between 5 pi over 6 and 7 pi over 6, that's only 2 pi over 6. So there isn't symmetry between these. But there is symmetry between this one and this one. That's only half a circle. And this one and this one, half a circle. So if I want to list these two over and over and over as I go around the circle, I only need one of them, which is pi over 6. And I'm only going to add pi n this time. I'm not going all the way around the circle. I'm only going halfway. Halfway around the circle is pi. So pi over 6 plus pi n will give me this one, this one, this one, this one. Now we need these guys back and forth. And it's the same thing. And this happens with tangent every time. Because tangent has a period of pi. It only repeats itself every pi unit instead of 2 pi. But I'm going to list this one, which is 5 pi over 6, and add pi n. Pi over 6 plus half a circle over and over and over. Okay? I did some color differentiation here. This one and this one over and over and over with symmetry. This one and this one over and over and over with symmetry. Okay? There is one more, but I promised you a 15-minute video, so I'm going to end it there. We'll come back. Actually, I'll have another video. I can't leave it like that. And I'll show you guys one little tougher example with symmetry. Keep grinding, keep getting after this stuff. Finish this marking period strong, and let's start the next marking period also strong. All right, see you guys. Moving on.